So far, we've looked at pH, we've looked at pOH, we've looked at finding the pH and the pOH of strong acids and strong bases. Then we introduced the idea of finding the pH or pOH for a weak acid. So today we're going to continue along that track, but this time we're going to look at finding the pH or the pOH of a weak base. So what we're going to do is we're going to look at our illustrative example of ammonia, NH3. And we're going to show how ammonia, whenever it's put into water, will dissociate into hydroxide and then its conjugate acid, ammonium. So if we were to write down the equilibrium constant for this, what we would end up having, our expression would be K is equal to the concentration of OH minus times the concentration of ammonium all over the concentration of ammonia. So notice this time whenever we write K, we actually have a subscript B. And that B just tells us it's the base dissociation constant. So this is just like what we've done previously with equilibrium constants, but now we're just looking at the specific example of the dissociation of a weak base. So here's a generic reaction where we use B to represent our base, and it goes on to form its conjugate acid, BH+, and then also hydroxide. So Kb in the generic form would look like this. Kb is equal to the conjugate acid times hydroxide all over the concentration of our base. And this generic reaction will hold true for these weak bases under the Bronsted-Lowry definition. So let's go ahead and look at some other weak bases. So we have ammonia, which is Kb is equal to 1.8 times 10 to the negative fifth. So what we'll end up seeing here is the general reaction for ammonia would look like this. Again, we'd have our base plus water, and then that would go on to form our conjugate acid plus hydroxide. And we could repeat this for any base. So now let's look at another common solvent, pyridine. So this solvent is basic. And it looks like a benzene ring, except now we have a nitrogen. There's a lone pair on that nitrogen. So in this case, we would have pyridine, which is acting as our base, plus water, going on to form protonated pyridine, plus hydroxide. So if you're going through and solving a problem, especially on a homework or an online quiz or anything, if Kb isn't given to you in the problem and it's required to solve the problem, you may have to actually look that up. So let's go ahead and go on and try a few numerical examples. So our first example is we're going to look at codeine. And in this problem, we're asked to find what the pH is of the solution. And I would urge you to go on and try to find the concentration of all the species that are remaining. So let's go ahead and write our chemical reaction for this. So codeine, we're going to abbreviate COD. We have plus H2O. And that goes on to form CODH plus hydroxide. So now we'll set up our ice chart. So we know the initial concentration of codeine is 0.0012 molar. We don't have any concentration initially present for the conjugate acid or hydroxide. We'll go through and set up our change, so minus x plus x, because the coefficients are all 1. So then at equilibrium for the COD, for the codeine, we have 0.0012 minus x. And we end up with, for our conjugate acid, x, and for hydroxide, x. So now, since we know what Kb is equal to, we can write out that expression. So Kb would be equal to our conjugate acid, CODH+, times OH minus all over COD. And then we could actually substitute in our values. So KB in this case is 1.6 times 10 to the negative 6th. Then our numerator will be x times x, so we'll have x squared over 0.0012 minus x. So whenever we go through and solve, what we'll end up finding is x is equal to 4.3 times 10 to the negative 5th. And since x is a concentration, we'll attach that unit of molarity to it. So x here is actually our concentration of both hydroxide and our conjugate acid. So since we're trying to find the pH, what we can actually do is we know the concentration of hydroxide. So we can find POH first. So POH would be equal to the negative log of x. After we plug in for x, we'll get the POH to be 4.4. But since we want to find the pH, recall that pH plus POH is equal to 14. So substituting in, we will get that pH is equal to 9.6. You already know the concentrations of our conjugate acid and hydroxide, so to find the initial or the equilibrium concentration of codeine, you would just take 0.0012 minus x. And you'll see that there's not a huge change in that value. Let's go on and try another example. So in this example, we're going back to our example of ammonia. So let's go ahead and write out the reaction for ammonia. So we'll have NH3 plus H2O yields ammonium plus hydroxide. Just like the preceding problem, we want to find the pH and the concentration of all the species present. Kb is given to you. So let's go ahead and start plugging into our ice chart. So the initial concentration of ammonia is 0.40 molar. There is no initial concentration of ammonium or hydroxide. So we'll plug in minus x plus x, because again, all of our coefficients are 1. So we'll end up with 0.40 minus x, and then x and x. So if we were to write Kb for this expression, Kb would be equal to ammonium times hydroxide all over ammonia. Whenever we substitute in for Kb and then for our concentrations, we'll have 1.8 times 10 to the negative 5th is equal to x squared over 0.40 minus x. So what we're actually going to do here is, because Kb is to the order of magnitude of negative 5 and 0.40 is to the order of magnitude of negative 1, we can actually completely ignore this x because they differ by more than 3 orders of magnitude. So now this simplifies the mathematical process. So we can plug in and solve for x. And what we'll find out is that x is equal to 0.0027 molar, or 2.7 times 10 to the negative 3rd molar. And this is equal to the concentration of hydroxide and our concentration of our conjugate acid ammonium. So if we want to find the pH, again, we know hydroxide, so we can find the POH. So POH would be equal to the negative log of OH minus, or in this case, the negative log of X. And what we'll find out is the POH is 2.6. And then pH plus POH is equal to 14, so we can plug in. And we'll end up finding that pH is equal to 11.4. So this concludes our examples on finding the equilibrium constant of a base and then using that to find pH or pOH. Hope it was helpful.